Day 38, Honors Physics, Statics, example number 5. And this is kind of the opposite of the problem number 1 with the traffic signal, or the one that was in the notes with the clothesline. And because of symmetry, there's a lot of shortcuts you can take here, because, well, T sub 1 and T sub 2 are one rope with one tension essentially, but you have your initial diagram in red there. The more important diagram is the diagram that I have here in blue. All right. By the way, this is a good technique that you could use if you ever get your car stuck in a ditch and you need to exert a force greater than your typical pulling strength, because what's going to happen is the rope is going to get tighter than the 500 newtons, which is like how hard you have to pull. The rope is going to be much tighter. In theory, this could work. And it has worked for some people. Anyway, you'll probably just call it a tow truck. But, that being said, if you look at the diagram here in blue, because of symmetry, the T sub 1y and the T sub 2y have to add up to 500, and they have to be equal to each other. So just by looking at that, these are each 250 newtons. And you really don't need to worry about both of them, but there's two of them there. Only because of symmetry here. If you look at the diagram, there's 13 meters for each rope. Everything is symmetrical. We'll do a problem next where it's not symmetrical. It's a lot more difficult. So now all I got to do is look at one of the component diagrams for either T sub 1 or T sub 2, and that will give you the answer for the other one. So if I take T sub 2, I'm looking how tight that rope is. That rope is pulling this way and this way. I really don't care about the X component, T sub 2x, because that's going to be canceled out by T sub 1x. But you could figure that out if you want to. But I know that this is 250 newtons, this particular force. I'm looking for T sub 2. Problem is right now, I don't know any angles, so I really need to look at the geometry of the situation in the diagram. In fact, if I draw that triangle, I'm going to go to the top here. The geometry of the initial setup. I've got 13 meters. It's 13 meters. And 13 meters. And then 24 meters across the bottom. But what I'm going to do here, because I want to figure out the angles, because the angles all will then match up and transfer to my force diagram here. If I split that with an altitude, I have 12 meters here and 12 meters here. And I'm looking for any of the angles involved. But, well, by the way, or I guess if I just look over here in the corner, theta would be an angle that I want to use. And if I look at the left-hand side of this diagram, half of that big diagram I have there at the top, the left-hand side, I'll highlight it in red. This triangle over here, which is a right triangle, I can just use cosine of theta. Cosine of theta would be 12 over 13. I can do inverse cosine to get the angle theta. So once I have the angle theta, which will be a small angle, I can transfer that over to excuse me, either one of my T sub 1 or T sub 2 component diagrams at the very bottom of the page here now. In other words, whatever that angle comes out to be, it will be this angle down here. All right, or going back up to the top diagram, there's a lot of symmetry up there, so this angle over here is the same as on the other side, which is the same as the angle on my component diagram at the very bottom of the page. Once you have that, then you can use sine or cosine, actually probably sine, to get T sub 2. And then you would have what you need.